Hello everyone, welcome to the Youth Research Institute podcast. My name is Allyson Fry-Petit, the founder of Youth Research Institute, and this is the show where me and some of my colleagues talk about recent scientific discoveries, review interesting research subjects, and interview researchers, professors, and graduate students about their research projects and how upcoming students can thrive in various research industries. Hello everyone, my name is Allyson Fry-Petit. I'm one of your hosts, and I would like to welcome you all to the first ever episode of the Youth Research Institute podcast. Now, this has been an initiative that has been in the works for a while now, and now that we've finally gotten the chance to create it, it's a great opportunity. We can help educate students around the nation about in-depth research and ways to get involved. For our first episode, we have a very fascinating subject for many people interested in chemistry, and one that I personally find really amazing because, I just was never exposed to this kind of chemistry, and something that I'm sure many other people would not be as aware of because we are studying and looking into the industry of solid-state chemistry. Now, before we get started and get into the meat and potatoes of this podcast, I'm going to give a short timeline real quick. So first off, I'm just going to spend the next about 15 minutes just talking about some introductory things, right? We'll be talking about what is chemistry, what is organic chemistry, how is that related to inorganic chemistry, and what is solid-state chemistry? Solid-state chemistry being a subset of inorganic chemistry. And once we talk about all these applications, all these different types of chemistry, we're also going to talk about a bit of computational chemistry and how that is applicable to certain industries or certain applications and research fields. Once we finish all that, we're going to move on to the interview with Dr. Allyson Fry-Petit, who is a solid-state chemist from Cal State Fullerton. In the end, we're just going to sum it all up with a conclusion, and then we'll just end the podcast episode from there. Now, let's get back to solid-state chemistry. I'm sure you can guess what it is. I'm sure some people might even know what the industry is. But for those who don't, let's start from the basics and move up from there. So, let's start with what is chemistry? Well, chemistry is most generally known as the study of substances. And substances can refer to a variety of things, including elements, as well as compounds. And if you don't know, a compound is just a combination of multiple different elements together. Now, chemistry is really interesting. I find it really interesting because it's just cool to study and learn about how our world works based on like the atomic level or the molecular level. And it's pretty fascinating to just look at different aspects of our life and how we can explain it with scientific means. But in general, chemistry is very applicable to many things. We can look at like the door in our house. It's made of wood. It's made of carbon. Not only carbon, but it has carbon in it. Or we can look into the air that we breathe. It has carbon dioxide. Or we can look at our bodies, where we have sugars in our bodies and has carbons. You might be wondering why I'm emphasizing carbon so much. It's because we are also looking into inorganic chemistry and organic chemistry. Well, first thing to note is that carbon dioxide in the air is not organic, and I'll explain what organic means in a moment, but I just like to point that out if anyone gets confused by that. But like the sugars in our body, or the wood in our door, or the food that we eat, they all have organic carbons. So let's talk about what an organic compound is. Well, first thing is that carbon is so common. I already gave examples of this. It's also in like many of our practical applications. We can see this through like our pencils, or we can see this in many materials that we use for construction. Wood, for example, as I mentioned about the door. And so carbon is like literally everywhere. It's very common and it's really important. And one of the most important aspects of it is the fact that it can make 4 bonds. Now, this is not necessarily important to our discussion today, but it's just a thing to know. But yeah, carbon is just really, really useful because many other things can't make 4 bonds, or make 4 bonds as well. And so having that capability allows carbon to be really useful and really applicable to many compounds. As a result, there was the creation of an entire category of compounds, an entire like subject or branch of chemistry based on carbon-based compounds. And that is what an organic compound is. An organic compound is one that's based on carbon as well as other elements like hydrogen and oxygen. But the main thing is carbon. But just to clarify, organic compounds tend to be characterized by the formation of a CH bond, or basically a bond between a hydrogen and a carbon. That's why CO2 isn't considered organic. But anyways, organic compounds, of course, are what constitute organic chemistry reactions and organic chemistry in general, and so carbon is really important. That being said, there are also many other categories of chemistry, like biochemistry, inorganic chemistry, materials chemistry, and analytical chemistry. And the reason why I bring up organic chemistry specifically is because I want to talk about inorganic chemistry. Inorganic chemistry is kind of like the opposite of organic chemistry, right? It's the study of inorganic compounds, which essentially just means chemical compounds that are not carbon-based. There's also some other compounds that get lumped into inorganic chemistry, like organometallic compounds. The point is that usually they're not carbon-based, and if they are paired up with other compounds that are metals, hence an organometallic compound. So yeah, that's inorganic chemistry, and inorganic chemistry is a pretty big industry, and it's pretty important because of the fact that many things are inorganic. For example, imagine our solar panels. A solar panel is obviously a really useful source of renewable energy, absorbs solar energy, but the capabilities of a solar panel is largely based on the element silicon. The way it works is that solar panels have semiconductors, and semiconductors are largely based on silicon, and it allows it to function really well. And so silicon is really important, and of course silicon is not carbon, and so semiconductors are based on silicon and are based in inorganic chemistry. We can think of any other chemistry with metals. For example, we might have a conglomeration of minerals, and we want to isolate some metals from those minerals, then that would also be a form of isolation through inorganic chemistry. We can also look at examples of many reactions that require metallic catalysts. What that basically just means is a catalyst is something that helps a reaction happen without being used up. And so metallic catalysts are really important and really useful, and so oftentimes those reactions are inorganic. Of course, some of those reactions are not inorganic, some of them are organic because the metallic catalyst helps the organic reaction occur, but there are also many inorganic reactions that use metal catalysts. So that's another example of a pretty good application of inorganic chemistry. Another thing that is more common, or I guess a couple more examples of more common applications, because you might not think of semiconductors every day. Something you might think of a lot is plastic. And ammonia, which is NH3, so it's based on nitrogen, is a major inorganic chemical that's used in the formation of nylons, fibers, plastics, and other pretty useful materials. So that's a obviously really obvious connection to our daily lives, right? We use plastic almost every day, or I would assume most people do. We can also talk about chlorine, where it is used a lot in agrochemicals. Agrochemicals, of course, meaning chemicals used in agriculture, so fertilizer, insecticides, or soil treatment. Of course, that's really useful for food. We need agriculture to eat, so obviously that's also another pretty common application to, or at least some indirect effect to, our daily lives. Now, this is all really cool, but what are we going to talk about today? So let's dial it down now. Let's narrow it down we narrowed down from chemistry into inorganic chemistry. Now let's narrow down to solid state chemistry, which is what we're going to be talking about. Now this is the specific stuff, and this is really cool. I think this is really cool. And we'll hear this more about solid state chemistry from Dr. Allyson Fry-Petit. But solid state chemistry is a form of inorganic chemistry that utilizes the analysis of solids. Now, of course, that makes sense. And it's pretty interesting because of the fact that solids are pretty difficult to deal with. It's a pretty tedious industry, I would say, because solids are difficult. They're less changeable, I guess is a good way to say this. For example, suppose you have a balloon, right? A balloon is full of gas. You can probably squish the balloon and put the gas under pressure and squish it, and it'll be able to change pretty easily, right? It wouldn't be that difficult. But now let's suppose you have a block of iron. You can't really squish that. I mean, you could try, but you're gonna have to require a lot of pressure. That should be really difficult. Same thing applies with temperature. You need really, really high temperatures to actually affect solids, like up to like the 800 degrees Celsius or higher, right? It's oftentimes much higher than 800 degrees Celsius. So it's pretty difficult to work with. It's pretty tedious, but it's very interesting and very applicable because a lot of the things we use are solids. Solid state chemistry teaches us about the properties, which is really useful for finding good materials for certain jobs. And so therefore it's really fascinating to study this subject. And yeah, we'll talk more about this during the interview. So I'm not going to go over it too much, but like that's just the general gist of it. Right? We're dealing with solids. It's a bit difficult, but it's teaching us about the properties of solids, and that's really key, because if we know the property of a certain material, then we're able to determine what we can use it for and what would be like maybe its downfalls or its good applications. On the other hand, if you're trying to determine what makes something useful, that would also be really useful, because if you determine what's useful about a certain material, then you can look for those same properties in other materials, and if you see the same property, you can be like, boom, that's something that's really useful as well. So yeah, solid state chemistry, really useful, and it's a really practical application. Another thing we're going to talk about in the interview is computational chemistry, and just the usage of computational things in science. It's just really practical, and one might think like, oh, when I'm thinking of chemistry or I'm thinking of biology, I'm just going to go into the lab and just like do a bunch of experiments, right? Like pour something into a beaker and pour something into a different beaker and then mix them, boom. Or like, I don't know, like throw something into a furnace and then let it cook and then like hopefully a reaction will happen, right? But oftentimes a lot of things happen outside of the laboratory in terms of computational things, for example. Computational chemistry is very, very key because, especially as we'll talk to Dr. Fry-Petit about, she is all about trying to create new materials and trying to find good combinations of different elements to create good materials that will actually exhibit the properties that they want. And computational chemistry is a really, really useful tool for this because, and just like computational tools in general, is really useful because it allows you to model things. For example, this is not really chemistry, but like one example that I'm more familiar with is Dft Calculations. What this is essentially that you take a compound and you model it, you like draw it out, and then you just run it through an algorithm. Using this algorithm, it essentially determines the most stable conformation of this molecule. I think this is really useful because it helps predict what would be a stable conformation of the molecule, of course, and it would help you determine the energy of the molecule, which is the free energy of the molecule. And using this free energy, you can calculate like what would be a reaction that would happen with a different compound. Dft calculations are useful in that sense. And in the same vein, not exactly the same exact thing, but in the same vein, you can use computational tools to model elements together in a solid. And when you create that solid, you can predict the properties of it with this computational tools. Of course, it's not going to be 100% accurate, but being able to predict what would generally be the properties would push you in the right direction as to what you'd want to study. So suppose you like combine element X and element Y together, and then you see the property that it absorbs light really well, and you want to find something that absorbs light really well. Then you're like, okay, great, we have a element combination that possibly has a high chance of having a property of absorbing light very easily. So let's follow through with this kind of study and look at solids with element X and Y and see how the properties match up. As you can see, the computational chemistry helps you kind of determine the right direction to follow if you're looking for a specific property. And of course, especially in this age where everything is digitalizing, having computational aids is always going to be faster and more efficient, and therefore is able to allow you to further science and further your progress much faster. Now that we've familiarized ourselves with all the topics at hand and all the topics that we will talk about in the interview with Dr. Fry-Petit, let's check out the interview.
Hello everybody, welcome to the Youth Research Institute podcast. I am your host, Ifan.
And I'm your host, Harrison, and today we have a very, very special guest from California State University, Fullerton. So, Dr. Fry-Petit, could you please introduce yourself a little bit?
Yeah. Hi, I'm Dr. Allyson Fry-Petit. I am a faculty at Cal State Fullerton, where I've been for 7 years now. I actually I study solid state materials, and we'll talk more about that today. I guess a little bit about my background. I am a first generation college student who started her trajectory towards a chemistry degree at William Jewell College, a tiny liberal arts school in Kansas City, Missouri. Then I did my PhD at Ohio State before doing my postdoc at Johns Hopkins, and then became a faculty here at Cal State Fullerton.
Interesting. So I guess before we get into like the nitty gritty, I just wanted to ask, like, did you have any like aspirations before becoming like a solid state chemist? Like, did you perhaps want to go medical school or any other subjects?
No, so I actually took a while for me to figure out that I wanted to be a chemist. I knew I did really well with chemistry in high school, and that was enough to spark my interest to go into chemistry in college. Once I was in my major, then I realized that I really loved research. And so I got involved in research in a bunch of different opportunities. And through doing that, I really honed in on the fact that I wanted to be a solid state chemist versus doing all the other types of chemistry that are out there. So that really helped. My multitude of research experiences really helped me narrow in on what I wanted to study.
Gotcha. So, well, I guess before we get to the nitty-gritty, could you please give us a little introduction of what a solid state chemist is? Because I'm sure many people don't know exactly.
Yeah, so a solid state chemist is a chemist, sometimes would be referred to as like a material scientist or a condensed matter physicist. And really all of those are just really focused on how do we make solid materials that are going to have a positive impact on people's lives. Right? So this can range from anything as simple as lithium-ion batteries in your cell phone or your computer to the materials that make up bullet trains or MRI machines, right? So it covers a wide variety of different solid things that we use day to day, right? But how we think about it, how we look at a material really is going to differentiate, are you a material scientist, which is more engineering, or are you condensed matter physics, which focuses on basic physics principles, or are you a chemist who thinks more about the compositions of these materials and how to make new solids that can be useful.
So as a solid state chemist, can you tell us a little bit more about like what your lab does in general?
So my lab, big picture, we are interested in trying to make new materials that can be useful, right? And so in my lab, we have a couple different avenues. Some of my students are working on, physically making materials by grinding up powders and heating them at very high temperatures, primarily. Some people in my group are more interested in looking at what we call data mining, which looks at the vast array of previous data that exists, saying, well, when we made these materials, what properties did they have? And can we correlate their structure, their properties, their composition, using a computer to help us then say, oh, this is the next new material we should make. And hopefully limiting the amount of time it takes to actually make a new material, because if we can identify exactly what we want with the properties we want, ideally, that would help speed up the process. And then part of my lab is also interested in how do we actually study solid materials? Because there are some aspects of chemistry and physics where we have a question that we can't answer because the technology doesn't exist to study it. So we also try and push the limits on how do we actually take measurements of solids. So those are kind of big picture what we're doing in the lab as far as like how we approach problems. But some of the problems that we're actually interested in, two of my favorites right now are, the first one is along the lines of how do we study materials. So one thing that I don't think I realized as a young chemist is that like solids actually move a lot, right? We don't think of that right now because like the couch you're sitting on, the chair you're sitting in, like you don't feel them moving, but they're actually moving quite a lot on the atomic level. And what's interesting is there's a lot of materials out there that how the solid actually moves is why its properties are important. Okay, so that's really interesting, but measuring that in a solid and correlating it to the structure is actually pretty hard. So my research group is trying to work alongside Oak Ridge National Lab in Tennessee to develop a method called dynamic pair distribution function analysis that really lets us visualize how atoms are moving when I put energy into them. So one of my students, Cody, he's a master's student. He's been with me about a year now. He's working on that project right now in collaboration with Oak Ridge National Lab and one of the national labs in the UK as well. So that's one project we're really excited about. Another project we're really excited about are something called oxygen transport membranes, which are materials that kind of do what it sounds like, they move oxygen, right? And so what is interesting about these is that these are used currently as part of the catalytic converters in your car. Ideally, catalytic converters that don't use things, precious metals. So maybe people stop stealing catalytic converters, but also would be more environmentally friendly as far as their usage. So they're used there. They're also used in separating oxygen from air, because actually that's energetically a very expensive process right now. So you can basically take oxygen and it passes through the material, or you pass air over the material and only oxygen passes through. We can collect the oxygen on the other side. So it's a really cool property. But what's interesting is these materials have been used since the 70s, but no one knows exactly how the oxygen gets through, right? They have a list of like, here are some good ones, you can use it for this, but why chemically that's happening isn't very well understood. So my group is doing measurements on how does the crystal structure, so the atomic arrangement of atoms, how does it change while you are heating the material or while you're applying an atmosphere around it that causes the oxygen to move. So those are two of my favorite projects right now. We have quite a few others, but
that's really fascinating. So you use a lot of computational work in your research?
Yeah, so we use computation in kind of two different ways. We use one to analyze our data, right? So after we collect all this great data, what do we actually, how do we actually know what it's telling us, right? So we use a lot of different computational tools to try and analyze our data. And then we use data mining to try and predict new materials. But we don't really do computation in maybe the same sense as others, where they're trying to predict properties or things like that beforehand. So a little bit different.
I see. So you're trying to study structure, like property relations, but by utilizing your experimental data and just like, kind of inputting that in. Okay, gotcha. Okay, that's really interesting. Yeah. Well, I guess just a separate question then would be like, how would you collect this data? Are there like specific techniques you guys use?
Yeah. So the majority of the data that we collect is going to fall into two categories: either structural information or spectroscopic information. Okay, so structural information is stuff that we're going to get from things like X-ray diffraction, neutron diffraction. This is when you can use something called Bragg's law to analyze the exact placement of atoms within a crystal structure. So we have that method, and we have some of those facilities here at Cal State Fullerton. Other facilities that we either have to travel to or send our samples to are Argonne National Lab and Oak Ridge National Lab, like I mentioned. So we use those facilities. And then the spectroscopic data that we use helps us understand additional information, ideally about connectivity of the atoms within the structure, so how they're connected. And so those are things like infrared spectroscopy, Raman spectroscopy, UV-Vis spectroscopy, and a lot of that we have here, and some we collaborate with others from across the nation and the world to get that data.
That's crazy. So you use like diffraction, X-ray diffraction you said, what was the other diffraction method?
Neutron diffraction.
Neutron diffraction. And you use that for analyzing like structure, and then you also use you analyze connections or like bond formation through spectroscopies.
Yes,
I
perfect.
see. And then you use both of those datas in data mining, and then you use that to like determine properties of the solid?
Well, kind of. So the data mining is a little separate, right? So the data mining is great for informing our decisions before we make a material. And then once we've made it, we use the X-ray diffraction and the spectroscopy to understand what's going on within that material. And then ideally, once we've characterized that and understand that material well, we can feed that information back into a new set of data mining questions.
Gotcha. Okay. And then you also mentioned this other project of using dynamic pair distribution function, you said. Could you talk a bit more about that? Like explain how you would use that, stuff like that?
Yeah, so that method is really interesting. So when we take a neutron, right? So a neutron is, part of the nucleus of an atom, right? If we take that neutron and we strike a solid, well, you have to speed it up, right? And then you strike a solid with it. Either the energy can go into the material and the material can respond in some way, or it can bounce right off, right? If it bounced right off in an elastic type process, that gives us diffraction, and that lets us know the crystal structure. If it puts energy into the system and I can measure the energy of that neutron when it comes back out, this gives us a form of spectroscopy. This is called inelastic neutron spectroscopy. And what happens in that process is when the neutron bounces back off, I collect that data. And what my student Cody does is he goes in and he takes our data that has multiple different energies that show us where we've created vibrations in the structure from that energy being absorbed. And what we can do is we do each energy cut. What we can do to that is we do a mathematical transformation called a Fourier Transform. And what it does is that then allows us to see the specific distances atoms are from one another in the crystal structure. That is a really interesting idea because we're not looking at the static structure where the atoms are, because I can do that with diffraction. We're looking at, once I've caused it to vibrate, how far are the atoms from one another, right? And we can actually visualize the distance. There's not another form of spectroscopy that allows us to do that. Every other form of spectroscopy looks at what is the response, how does a material respond to energy being put in, and it uses calculations to determine where did that energy go, right? Here, we're not relying on calculations that tell us where the energy has gone. Instead, we are actually seeing how far atoms are from one another. So I don't have to do a bunch of calculations. Ideally, I can just say, oh, look, like the atoms were 2 angstroms apart. Now they're 3 angstroms apart, right? That gives me information about what happens during the vibration process in a solid.
I see. That's fascinating. So instead of like studying the static structure, or like basically looking, like taking a photo of a solid, you're kind of like looking at how it's moving.
Yeah, exactly.
I see. Yeah, because of course, like atoms always move, or like unless you're like Kelvin or whatever. But like,
right.
But like in this case, you're studying the dynamic properties, and that's essential. And why is that important for?
Yeah, so it's really important. Have you guys heard of things called like superconductors?
Yeah.
Yeah, so superconductors are materials that have like, zero resistance to the flow of electrons, right? And so originally when I first started studying this, one of the materials we wanted to study was superconductors, because while we understand we can measure like high temperature superconductivity, we haven't fully proven why superconductivity exists, right? And so one proposed mechanism is something called a Cooper pair, where basically electrons and vibrations pair up within a crystal structure at very, very low temperatures, right? And so we were hoping that we would be able to see those vibrations the vibrations and electrons kind of pairing up in this process. So that was one of the reasons why we proposed it. Another area where we have used this is in something called the formation of a valence bond state. And what this is when as you perturb a system in some way, you see the bond structure changes significantly at, like, for instance, a very specific temperature, right? And what we could show was, by using this, we could show that it was not a dynamic formation of a bond, but was more of a static formation. And so that's it's a question that lots of physicists are very interested in. When I studied that, I was actually a postdoc partially in the physics department at Johns Hopkins.
Yeah, that's super cool. So yeah, I guess there are many practical applications to studying dynamic properties.
Right.
And when studying properties in general, and also just being like a solid state chemist, I guess just one question that I've always had is just like, what would be considered properties that are important, or like that you think would be useful?
Right. So some of the main things that we're interested in are, how do solids move electrons? How do they move ions? How do they interact with light? And how do they interact with magnetic field? Right? So if you can understand those things about a material, and also how do they move heat, right? If you can understand those aspects of a material, if you can tune those aspects, if you can control their existence, like in what materials they exist, you have the ability to basically form most of the technologies of interest to us, right? So for instance, if I'm interested in powering, a Mars rover, I need a thermoelectric, which is a material that is really great at thinking about how both heat and electrons can move in a material, right? And so I have to be able to tune those in order to have a rover that, doesn't have a constant supply of, electricity, for instance, right? So I need something like that. Or, do I need it to run my cell phone, right? Well, then I need something that is great at shuttling ions while letting electrons pass through, right? So those are kind of the properties of interest for most things.
Gotcha. And that makes sense, right? So movement of electrons is more like conductivity, I would assume. And then reaction to light and heat, I guess, would be like responses to the elements. Yeah,
responses to the elements, or for different potential uses, right? So if we think about maybe one of the most important materials going forward, if we want to think about how does solid state chemists combat climate change, would be something like solar cells, right? So how do we make materials that can use sunlight to turn that into energy, right? That we can use for electricity, right? So those are, how one-way materials would respond to light. That could be very useful to us.
Yeah, that makes sense. So then, many energy-related issues that you could solve as well. And also, lastly, your last project, you talked about the oxygen transport membranes and pulling out air. And so you said that the properties of these oxygen membranes aren't known, right? Mm-hmm. So then, what are you studying right now then?
So what I'm studying is, there's two aspects I'm studying. On the data mining side, my group is interested in trying to identify, are there better compositions that we should try? Are there better combinations of atoms that might give us a better oxygen transport system, right? So that's one aspect. But the other aspect that my group is employing is, we are actually monitoring the structure as we change the oxygen content in a very controlled manner. This is something that really hasn't been done a whole lot. To the best of my knowledge, there's only one other group in the US who has attempted to do this, where we actually use diffraction techniques under these types of conditions, and we monitor how the structure changes. Because if I know how the structure responds during the material's usage, I know how to improve it, right? Because when I have this amount, for instance, in the compound we're looking at right now, if I have this much cobalt, oh, that actually lowers the operating temperature, which is good for some situations, but it causes the structure to degrade in this way, which might be bad for other applications, right? So we're trying to really understand what is that relationship between the structure and the property, but not just the structure before it starts being used. How is the structure changing while we're using the material? And that's really an important aspect of, I think, what solid state chemistry looks like in the next 10, 15, 30 years, right? Is like monitoring how materials change in useful situations.
That makes sense. Yeah. So studying like how solids change while the processes are happening. I guess that also teaches you more about the properties of the solid.
Absolutely. Yeah, one of my favorite examples ever. I've never got to do this, but I've seen it done. There's a place at Oak Ridge where they want to study the diffraction, and they want to study like how materials break down. And specifically, there's an instrument there that they can like put an entire like airplane into, and then like scan parts of the airplane to like understand how it's changing. And like specifically, I've seen them have like whole engine blocks in there where they're looking at like engines that have failed in some way, and then they're monitoring the structure at like the fail point versus where it didn't fail. And that's really helpful for how we make new materials.
Wow, that's like straight out of like a sci-fi movie or something.
I know, right?
Yeah.
It's very cool.
That's crazy. That's super cool. And so I guess like, yeah, there's a lot of development of technologies that are being used for these, I guess, solid state chemistry as well.
Yeah.
So I guess just another question for, you talked about like the future of solid state chemistry. Like what are new technologies or techniques that are like on the horizon that you would expect to change the future of this field?
Oh, that's a good question. I think one of the areas that myself and our field as a whole has become very cognizant of is that most of our reactions currently are optimized at very high temperatures, right? So when I say high temperatures, the lowest we ever run a reaction in my lab is like 800 degrees Celsius,
Wow.
right? The highest is 1600 degrees, right? In my lab, but that doesn't mean that's the highest. Like other labs have higher capabilities, but that's energetically a problem, right? So I think we're very cognizant in our field of like, how do I start to lower the temperature of these reactions? But you also have to remember that a lot of the materials that we're making are effectively rocks, right? Like they're related to minerals, so they need high temperatures or high pressures to be made. So trying to combat some of that, the high energy cost of making our materials is something that's really important to a lot of people in our field. So along those lines, there's a lot of interest also in thinking about what are kind of the geopolitical nature that surrounds our materials. And what I mean by that is, if I'm making something from an element that I can only mine in a very specific part of the world, what effect is that mining having on that part of the world, right? Are they doing it in a manner that is destroying the environment, that's hurting the people that live there, right? Or if something were to happen and we were in some sort of conflict with that part of the world, would we lose all ability to make that technology, right? So there's a lot of questions about kind of some of the ethics around what materials we use and where we get them from, right? And so I think there's going to be fabulous new technologies, right? In my lifetime, I've been a solid state chemist since 2008. So really not that long of a period of time, but in my lifetime, I've already seen like a huge upswing in how we can think about photovoltaics or solar cells and what types of materials are used for that. So absolutely there'll be some of those things. But I think a lot of what my generation of solid state chemists are interested in is how do we better make some of the things that already exist in a way that's more green? And how do we make materials that can replace some of the very, very precious metals that are very expensive, very environmentally problematic?
Yeah, that makes sense. So studying a lot about using, or I guess like just in general chemistry, about like trying to be doing more practical chemistry. like lower temperatures, low pressure, more commonly used materials. That makes sense. That makes an immense amount of sense. So I think that's great. It's great to hear a lot about your research, and I think now we can move on to a bit more of like a student focused set of questions. So just like if anyone's watching and they want to like have questions for you, I guess one question that I would have would be like, how does a typical workday like work for you, I guess? Like, and I asked this specifically because I know that your research is very heavily dependent on some computational studies, but also a lot is like focused on synthetic efforts. So like, do you tend to spend more time on like computation or like outside of the lab, or do you spend more time in the lab on synthetic experimental chemistry based like studies? What's going on?
So as the faculty, I don't get to spend a whole lot of time in the lab ever, but my students, kind of what it looks like for them is that I like to have them trying to balance those things, right? So our reactions take a long time. So a lot of times what my students will do is they will set up a reaction and then maybe move more towards working on some of the computation side of things, or reading papers or writing. There's an immense amount of reading and writing that is involved in scientific studies, right? So they'll work on some of those things while the reaction is running, because a lot of our reactions take 24, 72 or 72 hours, right? So they take a long time. So they'll set up one aspect and then go work on some of the other parts, right? And they kind of try and cycle through those so that they're making the best use of their time. And so, but you're right, like when we're doing computational type work or data analysis, it doesn't have to be done in the lab unless it's like proprietary software that can only be on one laptop or one computer.
Gotcha. And I think that's also just like an important thing to be aware of, especially as like, since like YRI Youth Research Institute, we're trying to like expose students to like the broader range of like aspects of research and reading and writing, especially since I've had personal experience as well. It's a very important part of research, right? Like reading literature and understanding like things that you're doing, as well as just like making sure you have good notebook entries and all that stuff. Yeah, that's really fascinating, and it makes a lot of sense. Mm-hmm. Yufan, did you want to say something?
Yeah. So I was wondering, because you mentioned this in the introduction, how you really like chemistry in high school. I was wondering, like, what was it like beforehand, like before high school? Did you always wanted to? I mean, you kind of went over this, but I was wondering, how did you always want to go into this field?
Yeah, so I actually hated science. I really did. I did not love biology or earth science or really anything like that. For me, I loved math as a student. I loved it. I thought it was fabulous, right? Like the fact that there was like a right and a wrong answer. And when I found chemistry and physics, both of those were applications of the math, right? It was like, oh, like I can really see how math is really useful here, right? And so for me, that was really the spark. When I went away to college, I actually specifically went to a liberal arts school because I wasn't sure if I would stick with chemistry, from a sense that I loved a lot of things. I actually was in music. I played in band. I used to do a lot of visual arts sort of things. I really loved that side of my brain too, right? And what I think why I still enjoy, why chemistry kind of took over for me was because I could use my creativity and apply it in something that was more tangible for me, right? I was very good with art things, but I was never going to be like the next best musician, right? Like, but I knew that I could make an impact in science, right? By using both my creative side and my love for the connection of math to science. And so that really is kind of how I ended up here. But no, I think I tell my students this all the time. I think one of the worst things you can do for yourself is to say, like, if I don't know at 17 what I'm going to be the rest of my life, I don't know what I had no clue. I had literally no clue. I just followed what I enjoyed, right? And was like, I'm sure at the end of the day, I will get something useful out of this degree, even if I don't become a like lab scientist, right? And so I think people just need to be open to what they enjoy and whatever keeps you curious, right? I heard somebody say that the other day, like whatever keeps you curious is worth your time, right? And science has always done that for me.
Yeah, and also I think that's a really good point, that I think a lot of people have this misconception that if you're going to STEM, it's going to be like rigid, it's just going to be like really academic. But no, yeah, there's a lot of creativity in it, and I think that's a really great point that you bring up, and that's really interesting as well. And it's super cool that you like love music. Do you just like, I guess, separate question, like do you still do anything for music related?
I had it for a long time, but then last semester I actually played in the university band. They'll let faculty and staff play, and so I played last semester. I can't this semester because I have classes, but I did last semester and it was like super fun. So
Gotcha. What instrument do you play?
I play the flute.
Oh, that's sick. Okay, well, yeah, and then I guess also talking about like your past and like what got you interested. What do you think newer students should consider if they're planning on going into this kind of industry?
Yeah, so I think probably one of the areas maybe I'll phrase it this way. One area I wish I had learned beforehand, right? Because you'll learn all your science, you'll learn your math, things like that. I think learning a basic understanding of coding is really important because I basically had to teach myself coding when I started my postdoc at Johns Hopkins. And I did it, right? But I think there's so much more moving forward where questions we're asking is going to require some level of coding, right? Even just the data analysis that we use is much easier for my students if they have some basic level of coding knowledge, right? And we're not talking like you have to be super proficient in Python or something. No, like learning something like starting out with like MATLAB or Mathematica and learning basic coding it's like learning another language, and I think it's really beneficial.
Yeah, that makes sense. Yeah, especially since, you talked about yourself about like computational work, but also just lots of like biological sciences and chemistry sciences. Those are all like getting a lot more, not necessarily digitalized, but like a lot more technical, a lot more
absolutely.
Like, yeah, it requires a lot more proficiency in technology. Yeah, and a lot more computational work. Yeah.
Right, and like we just have to be able to analyze. And the thing is, what's amazing is our data sets are becoming massive, right? Just so huge. Like for instance, the data my students collect in my lab, if they put two data sets, like we want to overlay yesterday's run and today's run on the same thing in Excel, it crashes Excel. Like Excel can't handle it, and it's two data sets, right? So when I'm telling them, I want you to plot everything you've done this semester in one plot so we can see how things have changed, we can't, right? So we have to use MATLAB for it. So, my students learn it in my lab, but I think, learning that at a younger age is something I wish I had learned.
Yeah, so to add on, I was wondering if there's anything in addition to like coding, chemistry, and math, if there's anything else that high school students and like college students should focus on, any like extracurriculars or any other courses that they should focus on if they want to go into like a field like this.
Yeah, so I think one of, I don't know if there's a specific extracurricular per se, but I would say a lot of my job is actually networking, right? Learning to interact with others, right? So I go to conferences and having informal conversations with people around a dinner table, right? Or before or after talks are given. Feeling comfortable with that is not always the easiest thing, right? So I think it's a learned skill. So I think just being involved in something, right? I was involved in band. I got to know people. I talked to people who are different than me, and I learned some of those skills. And I think that's benefited me because in the long run, right? Like going up and talking to someone after a talk and being like, hey, I really enjoyed your science. I think we could collaborate in X, Y, and Z manner. Would you be interested in that? Isn't something that everyone feels comfortable doing, right? But it's really benefited me in my career, in my ability to get collaborations, to ask people questions where maybe they have a better understanding of what's going on in the problem I'm trying to solve and things like that, right? So I think being willing to try new things and get out there and interact with people that are different than you is just very important, right? And I think that can carry you a long way. So I think that's one thing. I think the other thing would be willing to say, I don't know what the answer to something is, but I really want to try and figure it out, right? So when I went from Ohio State to Johns Hopkins, the project that my PI at Johns Hopkins had for me, I had no idea what he was talking about. Like literally zero idea. And I already had my PhD in the field, right? And he was like, Allie, do you know anything about coding? Nope. Allie, do you know anything about inelastic neutrons? Nope. But I want to figure it out. I want to learn it. And it completely changed how I view my research, right? And how I have moved forward as an individual researcher.
Yeah, that's a great point that you bring up. Yeah, I think collaborating, having like people skills, just being able to talk, that's a really key skill.
Yep.
And yeah, thank you so much for talking to us. I think that brings us to around the end of our time. So thank you so much again, Dr. Fry-Petit, and I hope you have a good day.
You too. Thank you, guys.
Thank you so much.
And that was our interview with Dr. Fry-Petit. I will say that I learned a lot from our discussion, and I learned a lot about specifically solid-state chemistry. And in fact, I wasn't even aware that solid-state chemistry was a type of chemistry that existed before this interview. So I think it's a very interesting industry because, I mean, it makes a lot of sense, right? It's very applicable. It's a very commonly, solids in general are commonly used materials, obviously. And so learning about it is just really fascinating to see like the applications, the practical applications, as well as just like the studies that go behind it. So just to quickly summarize the entire interview, as well as like most of the podcast, we talked about Dr. Fry-Petit's research initiatives, and they're all really fascinating. I think it's really cool to see how they're trying to study materials and specific properties and how they're using computational tools to actually get this job done. And that also ties into the next point that I want to talk about, is like how we specifically had a great discussion about how computational tools are used in her research. This is just makes sense, and it just is super cool to see that, well, first off, in this era where computational tools are becoming more common, they're becoming more popular, and also many things are becoming more digitalized, it's really cool to see how computational tools are practically used in research, specifically chemistry. And so, yeah, I think it's really fascinating to see her use like different fascinating and really advanced tools like X-ray diffraction, or they talk about neutron diffraction, and how she uses dynamic pair distribution function analysis. All of these are really interesting computational tools, and once again, I'd just like to mention that our world's become digitalized. It's going to become much more key to use computational tools and learn how to do it. So of course, learning computer science will be pretty much mandatory in the future, unfortunately to those who don't like computer science, but I think it's going to be really key, it's going to be really cool, and it's just make research much more quick, much more efficient, and just a lot easier in general. We also talked about some specifics about Dr. Fry-Petit's specific work day to day, and so I think, and she also talked about her undergraduates and her graduate students and how they do their work day to day. So it's pretty interesting to see what life would be like in a laboratory in college, as well as possibly a similar industrial job or something like that. And we even had a chit chat about her music and her experience on flute and her connection to the creative arts and how that connects to science. And I think this is first off really key, because obviously science is not just a one-dimensional logical analytical thing. You also involve creativity in it, but also she plays the flute, and she's played in like a band before, and I think that's super cool. I play the alto saxophone as well as other types of saxophones, and Yifan also plays, or at least used to play saxophone. So it's super great to find a fellow musician among especially professional researchers. So that's really cool. So in the end, I hope you all have learned a lot today about inorganic chemistry, solid-state chemistry, and computational chemistry, and all of that jazz. And of course, I hope you got a deeper perspective into what chemistry can entail past just college and farther into later parts of one's life. So I hope you all have a great day, and I look forward to seeing you next week. To learn more about the Youth Research Institute and get involved, check out our website www.youthresearchinstitute.org and subscribe to our newsletter to become a member. You can also keep up with our content on our Instagram at Youth Research Institute. Thank you all for listening, and we'll see you next week.